Let me record this. Go ahead.
So this one, you're able to determine it's conservative.
He's not doing anything.
Determine whether it's conservative. Let's do it. Define the potential. Oh, good question. Let's do it. Okay. What we did yesterday was given a vector field, determine whether it's conservative. We have the vector field in two space. We determine whether it's conservative or not by taking the partial of n with respect to x and seeing if it's equal to the partial of m with respect to y. If it is conservative, that means it has a potential function for which the vector field is its gradient. And we can capture that potential function by doing a partial integration. And then we did it for three space too. We defined the curl. What's that?
You say that for the vector field, it's its gradient, the gradient of the potential function?
Yes. Yes. So, let's do this problem. What's the problem? What did they give you?
F of xy equals y times I plus x times j.
Okay, here's a vector field, yx. What it's doing is assigning a vector to each point in the plane. That vector is yx. Okay? So, we want to determine whether it's conservative or not. This is m, this is n. This is a homework problem. Partial of n with respect to x, 1. Partial of m with respect to y, 1. It is conservative. That means we can find a potential function. Here's how we find it. If we have a potential function, its gradient of this function that we're looking for is equal to our field yx. Well, how do you find the gradient to a function? Its partial with respect to x must be y. Therefore, this function is the integral of y with respect to x. If its partial is y, the function must be the integral of that with respect to x. And that is equal to xy plus possibly a constant that's a function of y. Well, what else do we know? The partial of our function with respect to y must be x. That's how we find the gradient, right? Partial with respect to x, partial with respect to y. If its partial with respect to y is x, the function then, its integral with respect to y, okay, we'll integrate this with respect to y to get xy plus a constant in terms of x. And what you have to do now is called reconcile the two. You have to come up with one function that meets both requirements. Well, it's pretty clear that our function then is xy. Okay? That's our function. What's the gradient of this function? Partial with respect to x, partial with respect to y. It's our vector field. Okay? That makes our vector field conservative. Yes?
I'm simple. Can you go in a little bit more detail, like the reconciling?
Well, the reconciling part is, you know our function looks like this, and it looks like this. You've got to come up with one function that meets both requirements. And in this case, since these are the same, that is our function. Often what will happen is you'll get something that looks different, but by coming up with one function, you'll be able to meet both requirements, like we did yesterday.
So you came up with that by taking the partial derivatives of each one?
I said that, okay, we know it's conservative, so I'm looking for its potential function. I know the gradient to the potential function has to be yx. That's what it means to be conservative.
Oh, so they have the same thing.
Yeah,
So if you got a different partial derivative for the f of y, then it wouldn't be conservative?
if we had a different answer here, if these two guys were different, it would not be conservative, and it would be impossible to come up with this potential function. But because these are the same, we know there is a potential function.
I see.
Okay?
Okay, I got
You got another one you want to do?
Could you do another example?
Yeah, go ahead. You got another one there?
Yeah.
Okay, let's do it.
Curl.
Okay, this is a three-dimensional one. Let's do this.
So
All right, go ahead.
I can read it out to you. So find the curl F for the vector field at the point 5, -9, 5.
And what is our...
Function is x squared times z times I minus 2xz times j plus yz times k. So that's the unit vector, right?
That's the vector field. What this is doing to every point in space is assigning some vector, okay? That's determined by the coordinates of that point. What we're going to do, first of all, we're going to find out if this is a conservative vector field by determining what its curl is. The curl of a vector field is its gradient cross product with the field itself, okay? What this means is you do I, J, K. Blush. Partial with respect to X, partial with respect to Y, partial with respect to Z, M, N, P. This is M, N, and P. That's the curl.
Trying to do both at once, it's just not gonna happen. We're gonna take it slow.
That's
Now
okay.
everyone's watching.
Wait, you got
Like,
this or what? You need some help? Liam, you want to?
Yeah, Liam, could you just?
Yeah, I got you.
All right.
This is why I need Dylan sitting next to me. You know.
That's why I said you're
Wait, how far are you going with this, Teddy?
I'm gonna stop.
All right.
It's like really warm in here.
All right. Okay. I'm just wondering. All right.
She's- I'm sorry.
Okay. Let's take a look and see what we have here. We've got. No, you don't. So what we have is M is x squared z. N is a negative 2xz. P is a yz. So, cross this out, cross this out. Now, this way, we're going to take the partial of yz with respect to y. What's that partial derivative of yz with respect to y?
Z.
Z. Minus. Now we do this one. We take the partial of negative 2xz with respect to z, and we're going to get a negative 2x. So it's going to be plus 2x. At that point in time, immediately, you could stop.
It's a non-conservative.
It's not conservative. Oh, but I think the question was to find the curl, not determine whether it's conservative. All right, so let's keep on going to find the curl. There's the x component. The y component. Cross this top out, cross this out. So partial of yz with respect to x, 0. Minus the partial of x squared z with respect to z,
So, x squared.
x squared. Okay, and that's a negative x squared, but it's the middle term, so it's you got to take the opposite of that. So this will be x squared, positive x squared. Yeah, gotta be careful with that. Cross this out, cross this out. Take the partial of negative 2xz with respect to x. Negative 2x. Negative 2z, rather, yeah. Negative 2z. Minus the partial of x squared z with respect to y. 0.
So
That is your curl.
Does that get entered in as a vector?
Do they give you the angle brackets or not?
I can do a vector.
They say it works like this, but they're
Oh, they want the i's and
Because
stuff?
it's I, J, and K. It's
Yeah,
just
use
vector.
the I, J, and K thing.
Okay, so it'll be z plus 2x for I.
Z plus 2x, quantity times the bold I. That's it. Oh, get that I out. There you go. What's that?
So is this stuff from sure you put that in? Was that like applicable to differential equations?
Diffie Q's in this, we use, this is X squared.
So how do you, like, what is this?
Zero.
Zero, okay.
So it's 0 minus X squared,
Oh,
but it's
for
the
J,
middle.
So it's negative, okay.
Yep.
And if
Burns,
so all of the numbers were zero, is that mean, or is it always?
If they're all 0, they have to be
Unless it doesn't like
identically
the
0
vectors.
in order for it to be conserved.
So
In Burns, it doesn't like it.
Right.
And it may be the, these things. Z plus X squared. Oh, at the point. We didn't do the point yet. Oh, we plugged the Oh, geez, we didn't do that yet.
All right, we got to plug them in. Okay, here we go. Sorry. We got the point 5, negative 9, 5. So we got 5 plus, we got 15. We've got an X squared of 25 and a negative 10. So you, in your notation, is 15I, 25J, minus 10K. Try that.
Does it actually curl? Or is it just a vector?
It's a vector, but you can see it on ones where the curl is not identically 0. The vectors will curve around the point. There's a tendency to rotate about a point when the curl is not identically 0. There'll be a point. Got it?
Yeah.
Nice. Woo. Yeah. Okay, what else you got?
That's it for now.
Okay, let's go on. You guys ready? Okay, here we go.
That was a heck of a problem.
That was cool problems. Good stuff.
That's good practice.
What's that?
I like summed yesterday up.
There you go.
Yeah.
Nice. Thank you, Dave. Okay, here we go. That was cool.
Thanks for time.
All right, I want to change tactics here a little bit and to go back to what we did the other day and look at this line integral. So here we have vector fields, conservative, non-conservative vector fields. What I'm going to do is talk about a line integral today, which seems like it's going to be totally different. And tomorrow we're going to put the two together. Okay, but today let's take a look at this problem. What we want to do is what I was mentioning the other day. If we have a wire, okay, and this wire has a density function, okay, a density function that's assigning a density to every point along that wire. Every ordered pair x, y has a density to it. The problem is to find the mass of the wire. Okay. Now, to find the mass of this wire, what we could do is do an approximation for a little piece of that by taking some arc length, delta S here, and taking the density function, let's say at this point, the initial point, and find the mass of this piece of the wire over that arc length to be the density function at that point times a length of the wire, a delta S. Okay?
What's the difference between those two density functions?
This is a density function. This is the density function at this point. This is the density function in general.
It's instantaneous.
Yeah, basically, yeah. The mass of the whole wire is going to be equal to the limit, as n goes to infinity, of the sum of all these pieces. Okay. That is a Riemann sum in S, the arc length, as opposed to a Riemann sum in terms of x, okay, down to the x-axis. This mass is the integral over this curve, okay? Over the curve, not to the x-axis, but over the curve. That's why this is called the line integral. Like I said, it's unfortunate that it's called a line integral, but it is. It's the integral over this curve of the density function ds. That's a line integral. The basic difference is, in our normal integral, we're taking rectangles to the x-axis with delta x's and summing them up and getting an integral in terms of x. In this one here, we're taking a density function over this arc length. If you consider the density function, this height here, we're summing up over the length of the curve is what we're doing.
From the curve to where?
What's that?
You go from the curve to where?
To curve up, straight up.
But like how high?
Yeah, I don't get it.
Yeah, what's that? No, the curve to the density function. Let's say the density function at this point is 2 grams per square centimeter. That's a density function.
Density function. How can you go to it if you're integrating it?
Great, say that again now.
You're integrating your density function. How are you supposed to go to it as your limit of integration if it's integrated?
What is this integral doing? It's summing up this height times this distance. Think of that as a rectangle now, pointing up from the xy plane. That rectangle has an area which is equal to the arc length times a density. We're summing up all those areas. That's what this is doing right here. And that sum will be the mass of the wire. Because every one of those rectangles, area, mass times distance, is density times the distance is a mass. So this area of this rectangle is the mass over that one particular piece, that little interval. It's a delta S times the density. It's the area, which is equal to the mass of that over that interval.
So it's kind of like we have a surface above the xy plane. We're taking a flat rectangle going up to the surface.
That's correct. And if it's curved like this, we're taking this rectangle, this rectangle, this rectangle, this rectangle, and this rectangle. It's like a sheet. We're finding the area of that sheet.
I don't want to accuse you of making stuff up, or anything, but I'm a little skeptical.
Yeah,
Yes,
I'm
we'll-
you right now.
I'm more of a visual learner, not a tutorial learner.
Well, what the heck? Oh, I wouldn't think that was.
There's the square, Dylan.
I know. I'd rather see like a 3D.
All right, hold on. Here we go. Okay, here we go. What's that?
There's no calculation of the arc in there.
Yeah, delta S is the arc length.
Uh,
Okay, watch this. Just watch this. You got a wire right here. I'm going to take this little piece of arc length times the density function. Now, I'm going to tell you, take the density function to be the height of this. Okay?
Is it just like some arbitrary square that's like, oh yeah, it's density?
Well, density can be anything.
It would be like a bar graph at this point, the bar graph.
Yeah, this here. Yeah,
And
exactly.
adding up all your, I get that.
Okay, you get that. Now, this one is the same height, obviously, but it doesn't have to be. Okay? Then I'm going to add up this one. And then I'm going to, if I had more hands, all right, I would add up another one here. I would add up all these things along the wire, okay, and add them all up. And what's the sum going to be? The mass of the wire. Because each one of these areas is an arc length times a density, okay? And that's a mass. This area would represent the mass of that wire over that interval. That's what I'm doing. You guys don't like this, do you?
Oh, okay. So it's just the line. It's not.
It's a line, okay?
And then
That's our curve.
So is that square really there, or is it just like
No.
representing it?
It's
Oh.
just, that square is just a number to represent the mass of that point.
That's what it is.
All right.
Take a density
All right.
times a length to get a mass of that piece.
I just don't get the limits of integration. How you go from C to the density function, then integrate the density function, and then the only calculation of the arc length is just going to be the ds. So shouldn't be your
That's it.
function representing the arc length that you're integrating?
Watch this. I'm not done yet. All right. I'm getting there. I'm going to get there. No, you're fine. I'm getting there. Now, how do you do this? How do you actually do this? Well, we can't. We're going to have to change this. We're going to change it.
I think I see the problem now.
Here's what we're going to do. Watch this now. I'm going to take this a different tact on this. Instead of having this wire in this path, I'm going to call the path R of t. I'm going to give the path a parameterization.
Okay.
All right? Now, there's my path, R of t. Whatever that path is, that's the wire. So, I'm going to change this limit to this limit. As n goes to infinity of this sum. Now, my density function, instead of being a function of x and y now, I'm going to change it so it's in terms of the parameter. It's in terms of t, and the y is in terms of t. And what is my delta s? Now, you recall what we did for arc length in terms of parametric form. This goes way back. That delta s is the square root of, remember what we did? We did a delta x squared plus delta y. That's exactly right. And we divided by a delta t. So we had a delta x over delta t squared. And we had a delta y over delta t. Am I still in the, up there?
Yeah.
Okay. Times a delta t. This part right here is my delta s, my element of the arc length. Because what is delta s? It's the square root of delta x squared plus delta y squared. And what did we do back then? We multiplied by delta t, and we divided by delta t in the form of the square root of delta t squared. Now, as n goes to infinity, what happens to delta x over delta t? It becomes
1.
no,
0.
no.
I give up.
Oh, Rex, you said it.
The derivative?
Yes, the derivative. You said it a minute ago. Because as n goes to infinity, the delta t's will go to 0, and that limit as delta t goes to 0, delta x over delta t is the derivative.
Oh, yeah.
Okay? So here's what we got. This is equal to this integral. So what we're going to do, instead of evaluating this line integral, we're going to change it to an integral in terms of the parameter. We're going to have our density function in terms of t. And what is our ds part? It's what we had from before. It's dx dt.
Where's the open that parentheses?
Right here and here.
Oh, I see.
Yep. No problem. dx dt, dt. Okay. And this is t going from A to B. This is the mass of that wire in terms of the parameter. It is nice. It's cool. Okay? And this comes directly about by our arc length here. Okay, you ready for this? Watch this. Now,
So-
go ahead.
Your original derivative, your limit of integration is going from the wire to something. It's not actually going to anything. We couldn't do it. Let's go on to the density function. However you want to explain it.
Yeah, okay,
So
go
now
ahead.
What we did was we created a parameter to explain the wire function in terms of x and y. We're calling it t now.
Okay, this is some function. This is something. This is some function here. That path. Okay, it's some y as a function of x. Okay, y is a function of x, and along that wire, okay, at every point there's a density function given by the row of x, y. So, but I'm going to change that function from y as a function of x, and I'm going to put a parameter on it. So I have x in terms of t and y in terms of t, and then that will define the path in terms of t. That's how we're going to change it from a line integral to an integral in terms of our usual integral in terms of the parameter t. So well, let's do a problem. Let's do a problem. Okay, you ready? Watch this. This is kind of cool what happens here. So let's take a wire. Like so. And now we're limited here, though. I got to tell you, until the integrals we can do, because what we're going to have to do is end up with this kind of a thing, and we have to be able to take the integral. And I've seen some integrals like this morning were nasty kinds of integrals. We don't want to get into really nasty. I finished one this morning. That one that we started yesterday?
Yeah, Teddy brought it to you?
Yeah, we did that one.
Trig substitution from static.
That was you I was helping you with?
No, not that one. I didn't do that one. No. That was two separate Z was telling me it's two separate ones. I said, Z, you do that one. I'm not, forget it. I'm not doing that thing. But that other one, we could do that one.
Yeah, just
Yeah.
a warm up.
Yeah. All right. So let's take a piece of wire, but let's take it in a linear path here. I know it's kind of wimpy, but let's take my height. We'll go to 6'2" here. Okay.
Wait, you're 6'2".
In my dreams, yeah.
I don't know, I was just kind of short.
You're 6'2" with heels on.
Yeah, big heels. Well, Tom Cruise apparently wears some pretty tall heels or something, right? All right, but anyhow, 6'2". We got a wire. Let's take a density function.
He likes to tie fiction novels that he, calls the Bible to his foot because, with the great Lord Cthulhu and whatnot, it's a science Christian thing.
Yeah.
That's how he.
That's how he does. Yeah.
It's science Christianity.
Yeah, he's a Scientologist, right? Yeah.
Actually, I think he.
Yeah.
I think he's not anymore. And they're like.
Oh, really? Scientology or whatever.
Or maybe that was whoever he was married to.
I don't know. I don't keep track of these guys.
It's
Yeah.
crazy stuff, but yeah,
It is.
That's how you have height.
Yeah, there you go. All right, so we got this wire along this linear, on this line. Let's do this. So the line is y equals, the slope would be 1/3 x. Okay? Okay, so that's the wire. That's the path of the wire. It's got a density function xy. So at the origin where it starts, there's no density at all. But at the end point, the density is 12 grams per square centimeter, whatever. Okay? We want to find the mass of this wire, okay, with its constantly changing density. Well, let's set it up. The mass is equal to the line integral of our density function over this arc length, over this path. Okay? What we're going to do is change it. We're going to change it so it's in terms of a parameter. In order to do so, we need a parameterization of the path. Can someone give me a parameterization of this path?
X equals T, Y equals 1/13.
Beautiful. That t is going to go from 0 to 6. That's perfect. That parameterization puts us on a linear path starting at 0, 0 and ending at 6, 2. Let's find out what the mass of the wire is. Mass is equal to the integral from 0 to 6. Now, what's x? T. Y, t over 3. The ds is the square root of dx dt, 1 squared, plus dy dt, 1/3 squared dt. Okay? That gives us a 1/3 to come out front. The square root, this is 1/9, this is 9/9. That's the square root of 10/9, the square root of 10 over 3. We're taking the square root out. I'm left with the integral of t squared dt. Check that out. That's 1 plus 1/9. That's 10/9, square root of 10. Yeah, okay. That's the square root of 10 over 9, t cubed over 3, from 0 to 6. That's equal to the square root of 10 over 27. 6 cubed is 216. 0 is 0. And we can certainly simplify this. 9 goes in there 3. 9 goes in there. Let's see. 9 goes in there 3. 9 goes in there 2, 18, 24. Oh, 8. 8 square roots of 10. Okay. That's the mass of that wire. But here's the thing. Liam gave us that parameterization, and it worked out really well. Let's suppose somebody else used a different parameterizations. After all, how many parameterizations of this path are there? There's an infinite number of parameterizations. Let's do a different parameterization and let's see what happens to our mass with a different parameterization. Now the only rules are these. We have to start at 0, 0, we have to end at 6, 2, we have to stay on the linear path. Okay? That's it. Can someone think of another parameterization that would work?
How did you find the first one? You just plug t in to the function?
What he did, yeah, what I think what Liam did, and he could speak for himself, is to let x equal t. That's the usual way of setting up a parameterization. Let x equal t and find out what y is.
I see.
Now that works, and that worked very well. But let's do a different one. Can someone give me another parameterization? Maybe involving trig functions.
Polar coordinates, make your r the hypotenuse.
Well, you could do whatever you want, but get it in terms of a single parameter t. But you got to use a single parameter. That's the thing. It has to be a single parameterization. I'll tell you what. Oh, you got one? How about this? Let's do a trig one. Let's let, let's see, as long as that's 1/3 of that one, let's let x equal, that's one, 6 sine t, and y equal 2 sine t. Does that work? Yeah, sure. And t is going to go from 0 to pi over 2. That should work. I think that'll work. Yeah, that'll work.
Could you use any points?
As long as you start at the beginning and end at, as long as you start at 0, 0, end at 6, 2, and stay on the linear path.
Because you use 6 and 1, 2.
Yeah, I got to start at 0, 0, but I got to end at 6, 2. So I use 6 and 2 to make this come out nice there. But you can use anything as long as you start at 0, 0, end at 6, 2, and stay on a linear path. This parameterization will stay on that linear path, okay? Because the y is 1/3 of the x.
Could you have done 3 sine t, 1 sine t?
Yes, I could have. Yes, I could have. And then I could have done it from 0 to, oh, wait, could I have done it? Would I have worked? Wait. So you're saying let x equal 3 sine t and y equal sine t?
Yeah, because
Oh, no, I couldn't do it. Because this will never get to be 2. So this is out. That's why, yeah. You couldn't do it with that. But I can do it with this one. You ready? All right, is everybody okay with this? You're,
What's our density function?
okay, here's what I did. What's that?
What's our density function?
Our density function is the same xy. What I'm doing the same problem, but I'm doing a different parameterization of that path. And here's what I did. All I did was to say that I need a function, a parameterization, where the y is 1/3 the x. And by letting x equal 6 sine t, the y equals 2 sine t, my y is 1/3 the x. And as long as I do that, I know I'm on a linear path, starting at 0, 0, ending at 6, 2.
well, then that's 1/3 that I had.
I know, but you can't get there. The sign doesn't reach it. The problem is this only can go halfway.
Yeah.
Yeah, so that was the problem with that one. Okay, you ready? Alex, you ready? All right, so here we go. Let's do it. The problem is to find the mass of this wire. The mass is equal to, here, it's the line integral of our density ds, just like before. I'm doing the same problem with a different parameterization. Now I'm going to use this parameterization. So the integral is going from 0 to pi over 2. The x is now 6 sine t. The y, okay, is 2 sine t. This is totally different. Square root of the derivative of this, dx dt, its derivative, which is 6 cosine squared, plus the derivative of this function, 2 cosine squared, dt. This integral is totally different than the other one. Looks nothing like it. Okay? This answer is going to be way different than the other one. All right? I know. Look at it. It's crazy. This is ridiculous. All right. I don't know. We got a 12 to take out front. I've got the integral from 0 to pi over 2. I've got a sine square. Oh, no. Oh, one of those sines to evens like we were doing, Teddy. Oh, no. And then we got a square root here. 40 cosine squared. Well, I can take the cosine squared out as a cosine. I have a square root of 40, which is 40 is largest perfect squared. It's a factor of 40. It's a 4 and then 10. Here, let me take it out, and I'm going to simplify it in a minute. Okay? So the 40 is 4 times 10. 4 is the perfect square. Square root of 4 is 2. So I get 24 square root of 10, right? 0 to pi over 2. Look at this integral. This is nothing like what we did before. This is totally different. This is way, way different. That mass is changing even as we speak. All right. So we got 24 square roots of 10. U substitution. What's U? Sine. What's du? Oh, there it is right there. So it's a u squared du. So it's u cubed over 3. Okay, u is sine, du is cosine. Very nice. Okay. This 3 goes into 24 8 times. Substitute in pi over 2 for t, and you get the sine of pi over 2, which is equal to 1. Substitute in the 0, you get 0. And look at what happened here. Let me bring in the other one, and let's see what happened here.
Wait a sec.
Bam. All right.
No, I'm not saying that.
Wow. There you go. Any one of those infinite parameterizations that are used, any one of them, the mass is going to be 8 square roots of 10. I don't care what parameterization you use, as long as you start at 0, 0, end at 6, 2, and stay linear along that path, okay? Doesn't matter.
Let's do like 10 more.
Coincidence.
A coincidence. It could be a coincidence. All right, I'll have you guys do one.
All right.
Here you go. Let's do exponential function.
All right, I'm convinced.
Great, yes.
I'm convinced.
You still copying that? All right. Let's do an exponential function. All right. What is it? Oh!
No, we're good.
No. I said, oh.
We got 2 minutes.
Oh, I got 2 minutes. All right. Well, then I can't let you guys do it. I'll have to do it out.
Ooh.
Wow.
Okay, you ready?
That hurts a little.
Oh,
you can bring it home.
Dan could do it in like 30 seconds.
Probably could, yes. No, I'm just, no, I,
Go ahead.
all right, I want you guys to do it, though. All right, I'm sorry.
I'm confused. What's going on right now?
Well, I told Brandon that I'd be done at 1:15 because he's got an important appointment. And
Oh, I'm sorry, Brandon.
but now,
No, you do you.
all right, let's do it.
Brandon, should I skip my lab?
I'm sorry. This is not his fault. This is not his fault. This is me. This is my fault.
Burns, just ignore this kid all class.
No, that is not.
Don't worry
No,
about it.
I am worried about him. I worry about each and every one of
Don't
you.
worry about it. I'll just bring it home.
Okay.
Fun tonight.
Okay. All right. All right. Let's set up a parameterization. Same problem. Let's do a different parameterization. I want you guys to do it, though. Okay. So what parameterization should we use? Let's use an exponential function, though.
E to the negative 5, that's supposed to
What is it?
Oh, is it going to be that one you put on the border?
Yeah, you gotta put like some factorials in there.
Oh, geez, no. We don't want to do that. But e to the 5x, I'll do an e to the 5x one if you want. Oh, wait. We got to be careful.
5t.
E to the 5t would be the parameterization, except
You can't.
You can't get the 0 one out of that. But if we subtract 1, we could. So oh boy, we're getting a little bit crazy here, but how about e to the 5t minus 1 and I want to end up at 6 though. I don't like it. I'm going to have to tell you, I just don't like it.
Alright.
I'm sorry. We could figure it out. What t value makes this equal to 6? What t value makes this equal to 0 is easy enough. That t equals 0 works fine. That gives us a 0. Well, let's do it. T equals 0.
Okay.
Now, I want this to be equal to 6. We've got to end at 6. So, I want e to the 5t minus 1 to be 6. E to the 5t equals 7. Take the natural log of each side.
How come it has to be 6? Just because you said so, or?
Yeah, because we said so in the beginning. We have to end up at the same place.
Alright.
So 5t equals natural log 7. So t is natural log 7 over 5. Okay. So here we go. You ready for this? Y is equal to e to the 5t minus 1 over 3. T is going to go from 0 to the natural log of 7 over 5. Is that right?
Yeah.
Okay. Okay, you guys do it. And the density function is what we had before. Oh, man. Go ahead. Find the mass of that wire. Then we'll be done. Oh, you have like 30 seconds to do it, too.
Hurry quick. We have all the time.
Who suggested it? Well, who said exponential function? Who's you did? Lame brain idea was that? That was me.
I don't know, man.
Oh, man.
Crazy.
Is it crazy? Oh. If Liam says it's crazy, it's
No, it probably
crazy.
isn't. I just started.
All right.
I thought Y's function being number 3.
Yeah. Well. Oh man, this comes out. It'll be great. What if it doesn't? It'll be.
I don't know if this is possible.
What's that?
No, it's.
It's impossible?
I think I get it.
You think you got it? That'd be great.
You just got believe in yourself, that's all.
Did you get E, Teddy?
Yeah. We need one person to get it done and say, yeah, it comes out just right.
It's probably gonna have to be R.Burns.
No.
Just getting Dan's here.
No, we got others. We got Dan, but we got others too.
Yeah, Jay's here too. Yeah, what's up?
We got you, Teddy.
Nah, I wouldn't bank on that.
That is not insignificant. Dan, did it come out?
I've got the integral done, but I need to do a bunch of arithmetic.
Oh, is it yuck then?
Would you like to?
Oh, I hesitate to see
Square some
this.
things, and this and that.
Oh, wait.
Oh yeah. So this times this.
I don't know if I'm setting it up right.
Scratch that.
Well,
Lordy.
So,
I'm passing this.
9 over 9.
Then the D is a 1. We need a 5.
Well, I'm going to do it. Let me.
Nasty.
It looks nasty. I'm going to do it. You got it?
I just want to.
You really? Well, this is pretty much what Dan has right there.
And that's just your substitution?
Yeah, to use substitution. It's pretty straightforward for me.
Just multiply 5 then?
Dan, he's got a 10/3 out front.
I'm confused about that.
I'm not sure what that is.
Yeah, me neither. 9 times that is 50 over 9. It's 10.
25.
What's do? No, we don't want to do that. We're going to do it out by hand.
You have 5.
I'm going to do it out.
Times radical 10.
Okay, you ready? What is it?
5/3 times radical 10 is what I've got.
5/3 radical 10. What'd you get? Radical 10 over 3? You're missing a 5 in there.
What
Oh,
do
yeah.
no,
After
I
you use
divide.
something-
Oh, I know it. Then the 5. Yeah, it depends on where you put the 5. That's true. I think you're both right. Okay, let me do it out, all right? You ready?
I called that.
Let's do it. Okay, the mass is equal to the integral of our density function ds. We have t going from 0 to the natural log of 7 over 5. We have x, e to the 5t minus 1. Y, e to the 5t minus 1 over 3. I'm going to take that 3 out. Square root of the derivative 5 e to the 5t squared plus the derivative, that's another 5 e to the 5t, but it's over 3. So you get 5 e to the 5t over 3 squared dt. Okay? So, here we go. We get 1/3. 0 natural log 7 over 5. E to the 5t minus 1 squared times. Now, I'm going to have a 25e to the 10t and then a 25e to the 10t over 9. I'm going to multiply this by 9 over 9. So that 25 times 9 is 225. I'm going to have a 225 e to the 10t over 9, 225, plus a 25 e to the 10t over 9 dt. What I did, I multiplied by 9 over 9 here. Okay, 5 squared is 25, times 9 is 225. I put it over 9 because I want to be able to combine those two into 1. So I have 1/3 integral natural log 7 over 5 e to the 5t minus 1 squared. Now, when I add these, I'm going to have a 250 e to the 10t all over 9, but I can take out and give me a 1/3 out front. Okay? So 225 plus 25 is 250 e to the 10t. With me on that? Okay. That 250 is 25 times the square root of, is 25 times 10. The square root of 25 is 5. I'm going to take that 5 out front. The square root of 10 that I get in there out. I'm going to have 0 natural log 7 over 5 e to the 5t minus 1 squared. I took the 250 out. I've got e to the 10t, the square root of which is e to the 5t. Okay, now I've got a u to the n form where u is e to the 5t minus 1. The du is 5e to the 5t. Well, this 5 I'm going to bring back in again and serve as my du. I'm going to end up with the square root of 10 over 9, okay, u squared du form, which is e to the 5t minus 1 cubed over 3. This is my u. The du is e to the 5t times 5, and that's where this 5 is helping out. This 5 is serving as the du. So I end up with this squared, which is this cubed over 3, from 0 to the natural log of 7 over 5. Okay, you ready? We're almost there. Okay, over 3. This 3 comes out front to be a 27. I'll have the notes here if anybody needs the notes, right? 27. Okay. Now, substitute in the natural log of 7 over 5. Okay, minus 1. I took the 3 out, so that's cubed. Okay, that's this one. And then I substitute in, and that's cubed, minus, okay, put in the 0. Each of the zeros 1, minus 1 is 0. Okay, I think. I think that's what happens there. Okay. 5s cancel. What's each of the natural log of 7? 7 minus 1 is 6. This is 6 cubed over 27. 6 cubed is 216 squared to 10 over 27. And 27 goes in there 8 times. Yeah. What?
Drop the pen.
You gotta drop the mic.
Drop the mic?
You gotta drop the pen.
No, it's too late.
Like this?
And leave the room.
Yeah, you got it.
There you go.
He was on the radio.
All right. Here's what we got. Bottom line is this. That line integral is independent of the parameterization of the tau. See you in a moment.
That's